All right, cool. Let's get this started. I believe this chapter is not going to be as long as the previous one, and we might even finish on time. So that is good. All right. So this chapter is more focused on liquids and what happens when you dissolve things in liquids, right? Let's start with a discussion of pure liquids. So just pure water or pure ethanol, pure whatever. You have a pure fluid, nothing dissolved in it. Well, if you take this fluid, whatever fluid you have, put it in a water bottle or whatever, and then put it out in the sun, what happens to the water bottle? Have you guys ever done that? Like a water bottle that you've put out in the sun, it's all warmed up, and you feel the bottle. What do you feel?
It seems to compress more easily.
Compress more easily. Put it out in the sun.
Yeah, I think that the bottle softens up, and then
True that.
the material gets softer, and then it's easier to squeeze.
That is true. The plastic gets softer. But if you have a little bit of water inside, have you guys experienced the bottle puffing up a little bit? Right? So what's happening is the water inside the bottle is evaporating, but it has nowhere to go, so the pressure builds up. But the pressure doesn't build up indefinitely. It will come to a stop. And for any liquid, it has a specific value of pressure at a given temperature. Right? So it doesn't matter how big your bottle is. It doesn't matter how much water there is inside. As long as it's the same temperature, all water bottles will build up to the same pressure, which is what we call vapor pressure. Right? So the pressure built inside a closed container at a certain temperature is the vapor pressure. Cool. So clearly, this vapor pressure depends on the temperature of the liquid. Oops. And so there's an equation that relates the vapor pressure to temperature. It's interesting because, yeah, like you said, the plastic softens up. And so if it was an empty water bottle, it would be more squishy, but because there's water, it actually puffs up. I know this more particularly because I come from the Middle East. I grew up in Saudi Arabia, and it gets really hot there. And so, you know, my family would often forget water bottles in the car. It gets super hot. You come back, and it's all like about to explode kind of pressure. So, okay. So that's what vapor pressure is. So if you have a certain temperature T1 and then you heat up the water bottle to another temperature T2 or cool it down to some temperature T2, let's say the vapor pressure initially was P1, the vapor pressure at the second temperature is P2, then these things are related via the, what is it, the Clasius-Clapeyron equation, CC, right, which goes ln P2 over P1 equals minus delta H vaporization 1 over T2 minus 1 over T1. Let me make sure I got the sign correct. Is that the correct equation?
I think there's a gas constant in there somewhere.
Right. Over R. Yeah, something like that. Let me double check. Yep. That is it. Yeah. If you want to keep the order of the numbers the same, you have to introduce that negative sign. You see it's P2 over P1, T2 minus T1. That introduces a negative. Another form of this equation is you distribute the negative inside, and so it becomes ln P2 over P1 equals positive enthalpy over R, 1 over T1 minus 1 over T2. Right, so two ways to remember this equation. Cool. R is the ideal gas constant. And remember, in different contexts, R can have different values depending on the unit. In this case, I like to remember the value of R. If the context is energy, then it is 8.314. Right. If there's any energy term involved in your equation, it's got to be 8.314. If there is some kind of liters or atmospheres involved in your thing, like volume. Let me take out atmospheres. If there's liters involved, some kind of volume involved, then you use the 0.0821. Here, delta H vaporization is the enthalpy of vaporization, which is a kind of energy. So remember to use 0.0821. Sorry, 8.314. Okay. All right, now let's take a quick look at all the variables in our equation. Pressure is a variable, both pressures, P1 and P2. The temperatures are variables, T1 and T2. And the enthalpy of vaporization, it's a constant for a given material, but it depends on the material itself. And R is just a universal constant. Okay. Right, so you've got 5 different things that you could solve for. So expect questions where you've got 4 of them and you want to figure out the 5th one. And those are all possible questions, mathematically speaking, that you can get from this question, from this equation. So let's make up a couple of questions. Let's say that a water bottle has a vapor pressure of 2 atmospheres at 35 degrees Celsius. 2 parts. Actually, I'll make it 3 parts. If the temperature is raised to something like 50 degrees Celsius, calculate the new vapor pressure. Second question. At what temperature does the pressure drop to 1 atm? And lastly, I'll make that a second question after this. All right, so yeah. 2 questions. Just to clarify real quick, this is often helpful. If you have a fraction involving pressures, right? If it's a ratio of pressures, then it doesn't matter what pressure units you use, because all pressure units, pretty much all pressure units are related to each other via multiple. So the multiple cancels out anyway, right? I think this was a question on Slack that somebody had asked. But it doesn't matter what pressure units you use, top and bottom. As long as they're the same, top and bottom, you're good. Yeah, go ahead.
Yeah, the issue with that was that when you take if P1 is equal to 1, so you take the ln of that at 0, so it kind of just it negates the pressure 1 in the equation. That's what I found. So like,
and that's okay.
I would get the questions wrong though, and then I converted to torr, and I would get them right.
Was this solving for two? Did you use the CC equation with P2 over P1 or just the P equation?
P2, the ln of P2 over P1.
And one of your pressures was?
If P1 was equal to 1,
yeah,
it would negate the entire, like, it would take P1 out of the equation and it would give me the wrong answer. So I had to convert to torr. I don't know why.
No, it should work. If your P1 is 1, then P2 divided by P1 is just P2.
Yeah.
And that didn't work?
No.
All right. Let me go over that question at the end of class because pretty sure it should work. Something went wrong somewhere.
Yeah.
Because the multiple has to cancel. There's no other way. Okay, so that's that. Temperature here, however, if you have delta T, as we'll see in the later section of this chapter, if it's a difference of temperatures, then you can use either degrees Celsius or Kelvin. It doesn't matter. Because those two are related by an additive constant. So when you take a subtraction, the additive constant cancels out. So the difference remains the same. Okay. Right, so P2 over P1, you can use any unit. I'm going to put an asterisk just to verify that it works in your case, Christopher. But delta T, a subtraction of temperatures, you can either use delta C or K. This is a reciprocal subtraction of temperature. So here you've got to use Kelvin. Okay. All right. So what's 35C in Kelvin?
298 or 308.
308, yeah.
0.15.
Yep, 308.15, approximately 308. And what about 50? Pavel, go ahead. I can't hear you again.
He wrote something in the chat.
Oh, yeah.
Can you hear me?
Yes, yes. So the equation that you've written is also the correct one, but it's equivalent to whatever. You see how your P1, your order is switched? It's P1, P2, and then T2, T1.
Yes.
If you do that, you don't have a negative sign.
I see.
Yeah.
Really? Okay.
Yeah.
That's all it is?
Yep.
So my version is also correct? It's an equivalent statement?
Think taking this negative sign and distribute it inside.
Well, I'm mostly concerned about what's in the numerator in the ln term.
That's okay. If you flip this, you introduce a negative. It
Right.
all works out. Yeah, it all works out. Yeah.
Okay.
Mm-hmm.
Thank you.
Yep. So just to reiterate, the equation that I have on the screen is equivalent to the equation that Pavel has in the chat. All right, cool. 50C, what is that in Kelvin? This should have been Kelvin.
323.
323. Thank you. All right, straightforward application. So ln P2 over P1. I think the vapor pressure, no, the enthalpy of vaporization of water is something you need to memorize. Okay, so it's about 40.65 kilojoules.
Sorry, you said that is something we should memorize?
I think Professor Wright is nice enough to give this value on an exam. But I think I've had to memorize it in the past. Usually stuff related to water, it's good to have in the back of your mind. All right, cool. Tell me what to do, how to do part A. Pretty straightforward.
You actually use 8.314
Oh yeah, over R.
joules per K. Joules per K.
Yep.
Oh yeah.
Yep. All right. So what do I do?
You have to plan. You have to understand what you're solving for. You're solving for P2.
P2. Good. All right. So give me other values.
2
2 on the bottom. Good. Uh-huh.
equals negative 40.65 over 8.314.
Uh-huh.
Bracket 1 over 323,000 or 323 Kelvin
323. Yep.
minus 1 over 308 Kelvin.
308. Good. Is this good? Any problems here? There's one problem.
You could, so for the ln,
Yeah.
you can expand it to ln of P2 minus ln of 2.
True. That's how you would solve. But there's an immediate problem with one of the values. Can you spot it? The temperatures look fine to me. The value of R looks fine. The pressure looks fine. Something is off about delta H vaporization.
You have to be in joules.
Yep. Yep. Let's get rid of that kilo, replace it with 10 to the 3 to make it joules. Exactly. All right. Now we've got a multitude of ways you can go about this. Like Christopher said, you could either use the fact that ln of a quotient, ln of a fraction is ln of numerator minus ln of denominator, or put this whole mess in a calculator. It comes out to some number. And your P2 over 2 is trapped inside an ln, E both sides. And so P2 over 2 is E to that mass. And so P2 is just 2 times that. Yeah. I think this is slightly easier than expanding ln P2 minus ln2. Yeah. But both work. Cool. All right, part B. Let's do this quickly. I'm going to start by writing down the equation. Ln, or you tell me what to write. Oh, my OneNote is acting up. All right. Right, here's the equation. What are we doing this time? All right. Grace, take a shot.
Sorry, I'm working on finding the answer for the last one.
Okay.
Is that something we need for doing the next part?
Nope.
Okay. Would we set up the equation again?
Yep.
Okay. So we have ln we can use one ATM.
Mhm.
All right,
Sure.
ln of 1 over 1 over 2
Yep.
equals same constant, same negative 40,
Mm-hmm.
0.65 instead of the third over the energy gas constant,
Mm-hmm.
8.314 joules Kelvin.
Mm-hmm.
1 over 35. I'm sorry, 325.
Let's keep track of, do you have a negative? Are you using the CC equation with the negative?
Mhm.
Okay, so let's keep track of our ones and twos. P1, T1, P2, T2.
So yeah, this is T2. So that's oh, I see.
Mm-hmm.
So that's X, 1 over X.
Yeah.
Minus 1 over 320.
Yeah. 308, right? That was the initial.
Yeah.
Yeah, 308. Cool. Thank you. All right. That is good. Man, why does this keep acting up? Ugh. Okay. Yep. And now it's just about solving that T2 or X in the denominator. All right. What do you suggest I do first?
I would to solve for T2, I would divide, I would figure out what this division is.
This blob?
Yeah.
Okay, let's just call that some number. Okay. Calculating the exact number is not important, just the strategy, okay. Right? Let's do the same thing here. Let's call this star.
Okay.
So now you've got star equals this number, 1 over T2 minus 1 over 3. Mm-hmm. What next?
And then I would distribute the number sign number.
You could. There's a better way.
Okay.
You want to get rid of that number. You want to isolate T2, right? So you don't want this here. Push it to the other side.
Okay. So divide.
Yep. Mm-hmm.
and then add 1/3.
Yep.
And then yeah, get rid of the 1.
Yep. Flip both sides. Right. So I'm running out. Let's say this comes out to a square. That's 1 over T2. Flip both sides. So T2 is 1 over square. Where this thing is square. Yeah. All right. Cool. Any questions? All right. A mystery liquid has a vapor pressure of 1 atm at 25 degrees Celsius and 2.5 atm at 40 degrees Celsius. Determine its enthalpy of vaporization. All right, Adam, you're up.
Okay. So for this one, it doesn't matter if we stay in Celsius, right?
Nope, you always got to convert it into Kelvin.
Oh, you do? Okay.
Yeah, just a straightforward subtraction, you don't have to worry, but this is reciprocal subtraction.
Gotcha.
Yeah.
All right, so 298 and okay, so ln of P2 would be 2.5.
Mm-hmm.
So 2.5 over 1
Mm-hmm.
equals delta H vaporization over the 8.314.
Yep.
Brackets 1 over 313
Mm-hmm.
minus 1 over 298.
Yep.
And okay, so I would solve the ln 2.5 over 1.
Yep. Let's call that something.
That's something. Then I would solve what's in the brackets, the temperature
Mhm.
situation.
Yep.
And
Let's combine it with this guy. Yep.
okay, and then perfect. And then you just divide by number
Yep. And put a negative.
and put a negative.
Cool.
That's it.
That's it. So that gets you something. And of course, remember the units. Standard unit of this thing is joules. If it turns out to be a pretty large number, might make more sense to cast it in kilojoules. Right. But okay. All right. So this is good. Just a small trick question. We don't have to do it. As the pressure, no, as the temperature is increased from 10 degrees Celsius to 20 degrees Celsius, the pressure increases. Oh no. As the temperatures increase from 10 degrees Celsius to, let's say, some mystery temperature to 2 degrees Celsius, the pressure increases 5-folds. And we're talking about water as the liquid. As the temperature of water is increased from 10 to T, the pressure increases 5-folds. Determine T. Christopher, want to take a crack?
How we'd set this up,
Yep.
or is there like a straight up?
Nope. How would you set this up? We're restricted to the same equation. No magic tricks, just application. Let me change increases because to becomes 5-folds. Yeah, go ahead.
Can I guess?
Yes.
Would it be ln5?
Yes.
Okay.
So if the pressure becomes 5-folds, all I'm saying is that the new pressure is 5 times the original one. And so P2 over P1 is 5.
Abdullah, is that something we would see like the folds? Like what does that mean?
Oh, 5-fold simply means it's increased by a factor of 5.
Okay, so folds is equivalent to times.
Yeah.
Oh, okay.
Yeah.
Okay.
It's like if you buy tissues, tissues say 2-ply. That just means it's double layer. Yeah. It's like that. Yeah, 5 folds.
Okay.
Yeah. Yep, straightforward. Okay, cool. So we're done with pure liquids. We know pure liquids like to have some pressure at some temperatures. And if you change the temperature, the pressure changes. So we're good. Now let's talk about solutions. Let's adulterate our pure liquids by adding something to it that dissolves. Sugar, salt, glucose, whatever. Okay. First question to ask is, well, how strong is your solution? How much stuff have you added to your solution? Is it dilute? Is it concentrated? Right? So the first thing that you want to talk about is the concentration, the ways to put a number to the concentration of a solution. Concentration measures. Very quickly, what is a solution made of? There's 2 parts to a solution, right?
Solute. Solvent.
Yep, solute and solvent. And what's solute and what's solvent?
Solvent is the larger or the one that's in more presence.
Yep, exactly. This is big, this is small. Some people think of solvent as liquid and solute as solid, but no, because you can have solutions of liquid with liquid. And so then it just becomes a matter of which one is present in more quantity. All right, so there's we're going to learn about mole fraction, mass percent.
Just a question.
Yeah.
Is this small and big? Is that in terms of volume or moles?
Excellent question. I don't know. Because you could have a situation where you have more moles with less volume, right? Oh, good question. I don't know. Yeah. Huh. The question will often, if there's room for ambiguity, it will specify which one to take as the solvent. Because at the end of the day, it's an arbitrary choice. This is just a helpful convention to have. But if there's like confusion, just, yeah, you specify and move on. Okay, mole fraction, mass percent, molarity, and molality. 4 ways of putting a number to the concentration of a solution. Mole fraction, as the name suggests, is, so you have, let's say, components A and B to a solution. And so the mole fraction of component A is just the moles of A divided by total moles, which is moles of A plus moles of B. And similarly, the mole fraction of B is just the number of moles of B over total. It's like what fraction of the total comes from my component. That's the idea. Right, so I'm just going to write total is moles of A plus moles of B. So fraction means this. Percent means take this times 100. Right? So mass fraction would look like this. Mass of A over total mass. But if you want mass percent, just multiply the fraction by 100. And so this is mass percentage of A. And similarly, mass percentage of B is the fraction mass of B over total times 100. Molarity has denominator of liters. Molality has denominator of kilograms. That's the main thing to distinguish. Molarity is big M. Molality is little m. Big M equals moles of solute over liters of solution. And molality is moles of solute. So the numerator always remains the same over kilograms of solvent. Also, 2 key things to distinguish is that molarity involves solution on the bottom. Molality involves solvent on the bottom. Crucial difference. And I'll give you a question where that distinction is important. Oftentimes, you will use this little relationship, not relationship, an approximation. If you have a bunch of water and you add some salt to it, does the volume of the water really change that much? Not really, right? So you can often approximate, especially in solid plus liquid solutions. Solid in liquid solutions, that the volume of the solution is approximately equal to the volume of the solvent. And I'll give you a question where that's important. Okay. Once we're done with this topic, we're done with 2/3 of the chapter. Colligative properties, that's the last thing to discuss. Okay. All right, let's do some questions. You've got, let's say, 30 grams of glucose in 100 or 1,000 grams of water. I'm just going to very quickly tell you glucose is 180 molar mass. Water is 18. Yeah. just so you don't have to go ahead and calculate it. All right, so let's throw everything at it. Calculate the mole fraction of glucose and water one by one. Calculate mass percent of glucose and water. C, calculate molarity of solution. I'll start with molality. And calculate the molarity. This is one of two questions I'll give you for this topic. You know what? Let me change the grams real quick just to make them nicer numbers. I'll make glucose 360 grams. And I'll make this 18,000 grams of water. All right, so I've changed some numbers here. Okay, how many moles of glucose?
Two.
Two, good. And so mole fraction, oh, by the way, mole fraction denoted by this, yeah, that symbol. It's the chi. So chi glucose will be equal to, tell me.
I'm sorry, I think I missed something. Why is it 2?
Uh-huh. Okay, so let's calculate moles of glucose. So moles of anything is its grams divided by molar mass, right?
Mm-hmm.
Two.
Oh, that's the, oh, okay. Sorry, thank you.
Yep, all good. All right, similarly, tell me for water what it is. I've made the numbers nice.
$1,000.
1,000. Great. Cool. All right, so what do I write?
2 over 1,002.
1,002. 2 over 2 plus 1,000. Yep, 2 over 1,002. Great. All right, somebody else tell me how to do it for water. Grace?
It'd be 1,000 over 1,002.
Yep. Pavel? B?
I'm looking at B right now. It says mass percentage of glucose and water.
Yep, so one at a time.
Mass percentage. Okay.
Yeah.
Okay. So for mass percentage, what's the symbol that you use to
Percentage of water.
percentage of water? Okay.
Yep.
So we have we're gonna have 18,000 grams water divided by the total, which is gonna be 18,300 grams.
18,360
I'm sorry, 18,360 times 100.
times 100. Excellent. And the other one?
And the other one would be 360
Yep.
divided by 18,360.
Yep.
times 100.
Good. Yep. And now since it's a fraction, it doesn't matter if they're in grams, kilograms, as long as you're consistent. Yeah. Okay. All right. Moving along. Alexandra, tackle C.
Okay. We want molality
Mm-hmm.
is the moles of solute. So the moles of glucose,
Mm-hmm.
which are 2,
Mm-hmm.
divided by the mass of water, but in kilograms, which
Mm-hmm.
is that going to be the 18,000 divided by 1,000?
Yep.
Okay,
Yep. Exactly.
great.
So 18.
Yeah, 18.
Great. We're done. All right. And who else is here? All right, Christopher. Last one, D.
Similarity is moles of solute over liters.
Mm-hmm.
So moles of solute is 2.
Mm-hmm.
And then
What's the density of water?
I think it's 1.
Yeah.
So it'd be 18 liters.
18 liters. Good. So let's just explore that. 18,000 grams. It's the density of water is 1 grams per milliliter. So you can convert grams directly to milliliters. And then, yeah, convert to liters, divide by 1,000. 18 liters. But the problem here is the 18 liters is the volume of water, not water and glucose added to it. Right? But they're about the same. So this is the approximate answer. Good enough. Yeah. The real volume of the solution might be slightly larger than 18, or actually it might also be a little smaller. It's counterintuitive, but sometimes adding a solute actually shrinks the total volume. That happens, if you're curious, when the attractive forces between the solvent and solute molecules is stronger than the attractive forces between just the solvent molecules themselves. So it's like it gets pulled in on itself more tightly.
That's crazy.
Yep. I wish I had an example. Don't, but okay. Oh, one more question, and then we can move on to colligative properties. How are we doing on time? Oh, pretty good. A solution. Pavel, go ahead.
I would like to ask you, could you please raise your screen up to where you drew that very helpful table so I could take a screenshot?
The very helpful.
Yes, describing all the different concentration parameters right there. Okay, please hold.
Sure.
Thank you very much.
Yep, no problem. And of course, you'll also have a recording today. Solution of, everybody knows where to find the recording? Yeah?
Yeah.
Okay.
I don't. If you could please be so helpful as to provide it, that would be appreciated.
It's on, I put it on the, okay, so if you go to your Slack, let's see. and you go down to recitation. On the top, you'll see this takes you directly to the Zoom one-click button. And if you click on this, it takes you to the YouTube playlist that has the recordings. If you can't find that, I'll just put the link to the playlist in the chat. Oops, made a mistake. This is the correct one. Okay. All right, solution of sulfuric acid has a density of 1.3 grams per milliliters. Yep, right. If the molality no, let's go with molarity. If the molarity of the solution is 3 molars, calculate the molality. Okay. This is a tricky one. Not too much. Very limited information, right? You only have 2 numbers to work with. Density and molarity. It seems like we're in need of more numbers, so let's make up a number. Now, molarity, all of the concentration measures are fractions, right? They're ratios. So it doesn't matter how much of the sample you have, right? If I have a big, huge vat of sulfuric acid, it's going to have the same concentration, same molarity, same molality, and all the other things, compared to if I took a tiny test tube sample from the same batch, right? So the concentration doesn't depend on the amount of sulfuric acid or whatever solution you have. So it's up to us. We are free to choose some value. It will always work out, right? So here we want the molality of the solution. We have the molarity. Molarity relates moles and liters, right? Pick some amount of sulfuric acid. Let's say a liter of sulfuric acid. Take a liter of sulfuric acid. Without thinking, quickly tell me how many moles of sulfuric acid have I got?
3.
Yep, 3. Right? Because molarity is moles of sulfuric acid per liter of solution. That's why I took a liter. You can take 2.5, whatever, but then you'll have to do the math to figure out the corresponding moles of sulfuric acid. So take convenient numbers like a liter. Okay. So you've got 3 moles of sulfuric acid. Perfect. Great. So we have for molality the numerator already. That's good. Just going to write this down here. Molality. I know what goes on top. It's 3 moles. Okay. By the way, it's not a liter of sulfuric acid, but a liter of sulfuric acid solution. And just for your convenience, I'm going to give you the molar mass of sulfuric acid. I think it's 98. Okay, so what are we missing?
Kilograms of solvent.
Kilograms of solvent. Yep, that's exactly right. Okay. So let's see what we have. We have a volume, which is 1 liters. We have a density, which is 1.3 grams per milliliters. What is the volume of? Is it of the solvent, is the volume here the volume of the solvent, the solute, or the solution? What's 1 liters?
Solution.
Solution. What about the density?
The solvent. No, solute.
Nope. A solution of sulfuric acid has that density. They're both informations. They're both values for the solution. Cool. So they're compatible with each other, right? What is density? What's the formula for density?
Mass over volume.
Mass over volume. And since we're talking about solution, now density of solution is the mass of the solution over volume of the solution. We've got that and we've got that. Which means if I solve for the mass, I can just plug in the numbers and figure it out. 1.3 grams per milliliters times what? Yep. Christopher?
Times 1,000 milliliters.
Yep. Don't write 1. Make sure your units are consistent. Yep. Milliliters go away. And so you end up with 1,300. No. Yeah, 1,300 grams. Excellent. This is the mass of the solution. But that can't go in the bottom of the molality. We need the mass of the solvent. But the solution is composed of solute and solvent. So this is the combined mass of solute and solvent. If we could just take away the mass of the solute, we'd get our required mass. Any way to figure out what the mass of the solute is? Okay, let me just write that SOL is solution so as to not confuse it with all the other SOLs. Okay, so we have 1,300 grams of solution. What's our solute here?
Sulfuric acid.
Sulfuric acid. What do we know about sulfuric acid?
There's 3 moles of it.
Cool. So tell me the mass of sulfuric acid.
So you would do, you could find the molar mass.
Yep.
Or you could use the molar mass rather.
Yep. So it's 3 times 98, right?
Yep.
Moles times molar mass gives you the grams. I'm just going to say that this is about 300, and I'm just going to call it that. Yeah, too lazy. Okay, 300 grams of solute. So what's the mass of the solvent?
1,000 grams.
Yep, about 1,000 grams. It's the subtraction, right? Cool. Which is 1 kilogram. And we're done. Yep. This is probably the hardest question from this topic that you'll find. Okay. All right, just to reiterate, you have information about solution that you use to calculate the mass of the solution. But what you're interested in is the mass of the solvent. But you have information about the solute that allows you to calculate the mass of the solute. So if you just do solution minus solute mass, you get the mass of the solvent. Okay. And of course, if you have, in all of these questions, you can always start with a certain molarity or molality of the sample to, a certain volume or kilograms to work with. Because they're all ratios and it doesn't matter what you start with. Okay, cool. All right, so last topic deals with something very interesting. Now that we know how to classify our solutions depending on how strong or weak they are by putting a number on it, let's talk about what changes physically when you add a solute to a pure liquid. When you start with a pure liquid, of course, pure liquid has some boiling point, some melting point or freezing point. It has some pressure, vapor pressure, and it will also have some what's called osmotic pressure, which is 0 to begin with. Tell you what osmotic pressure is. But you have these bunch of physical properties about a pure liquid. Now the idea is you add a solute to this liquid to make a solution. How do these 4 things change? They do change. Yeah. And so the changes are characterized by these 4 colligative property equations. First one is delta TB, change in boiling point is I times a constant KB times little m. Change in freezing point is negative I times KF times m. The vapor pressure, I'm just going to say this. The pressure of any component, let's say some component A, is given by its initial vapor pressure times its mole fraction in solution. Okay, and I'll expand on that in a second. And the osmotic pressure is given by, oh, there's an I here too. I forgot about that. All of these equations have I's on them. The osmotic pressure is given by I times RT times big M. Now, qualitatively, what happens when you add a solute is that the boiling point goes up, the freezing point goes down, the vapor pressure can go either way. Actually, it does go down, the vapor pressure of the solvent itself. We're not talking about the total pressure of the solution. That might go up or down. And the osmotic pressure goes up. So these are the qualitative changes that happen. And if you want the exact amount of change, they're given by these 4 equations. The deltas in each case represent solution minus like solvent. Right, so the delta TB would be the boiling point of the solution minus the boiling point of the solvent. Delta TF, freezing point of the solution minus freezing point of the solvent, and so on. Delta TF has a negative in front of it because it goes down. Pavel, question? No, okay. I like to remember these four equations in this format. They always look like this. All four of these equations have the same exact structure. They start with I times a constant times a concentration measure. Right? All of them start with I. They're followed by, if you have a boiling point question, you have the boiling point constant. If you have a freezing point question, it's a freezing point constant. Pressure, it's the initial vapor pressure, which is the same for a given species. And then the last thing, the constant is the ideal gas constant times the temperature, followed by a concentration measure. In the first two, it's molality. In pressure, it's mole fraction. And in the last case, it is molarity. That's how I like to remember. Same structure. Okay. I is called the Van't Hoff factor. It simply tells you how many pieces your solute breaks into upon dissolution. Okay, let's work on that real quick. NaCl. What does this break up into on dissolution? It separates into its ions, right? Yep. Na plus, Cl minus. That's two pieces, so I is 2. What about magnesium iodide? How many pieces does this break into? 3. 1 magnesium, 2 iodines. 1 piece here, 2 here. What about glucose? C6H12O6. Yep. Glucose doesn't break up. It's a covalent compound. Only ionic compounds break up into their ions. So this remains as is. So it's just a single piece. I is 1. Okay, so we have a general rule now. If you have a covalent compound, I equals 1. If it's ionic, you just break it up into all of its ions and it's that. However, you can have ionic compounds like silver chloride that are very mildly soluble, sparingly soluble, right? And so this thing, it is true that it breaks up into Ag plus and Cl minus, but it's an equilibrium. It's a very small amount of Ag plus breaks up into, very small amount of AgCl breaks up into Ag plus and Cl minus. The Van Hoff factor is not just how many pieces solid breaks up into, it's the average number of pieces, right? So if you have 100 AgCls, how many of them break up into their ions, sort of thing. So if AgCl was a highly soluble substance, then it would be 2. But since it's not, it's something less than 2, but more than 1. 1 would say it doesn't break up at all. 2 says it completely breaks, but it's partially soluble, so it's partially breaks. And so I here would be, I don't know, 1.2, something like that. You will not be given a question with AgCl where you have to know what I is. You may be asked to solve for I given everything else. Okay. So the general rule is that if you have a completely soluble or highly soluble ionic compound, then it's just counting pieces. If it is partially soluble, then it's complicated. Highly soluble, count pieces. Partially soluble, it's some decimal number. Cool. All right. Yeah, so that's that. Little m is molality, big M is molarity, chi is mole fraction. Mole fraction specifically of the component A. All right, so let's look at some questions. By the way, osmotic pressure, if you want a just a quick intuition on what that is, it's this. Okay, imagine you have a tank and you have what's called a semi-permeable membrane, something that allows water to pass through but not solute. Like imagine you have salt water. This is how salt water is separated into pure water. Suppose you have on one side, you fill it up with some salt water. And on the other side, you fill it up with pure water. Right? So there's no height difference. So there's no pressure difference on each side, but one is salt and one is pure water. You guys remember osmosis from biology or something? Right? Osmosis, water flows from fluid flows from higher concentration to low concentration, high to low. That's why when you have that's how raisins, if you take grape and put it in salt water or sugar water, it will shrink up because water moves from higher concentration. Oh, no, it's the opposite. Water moves from low to high. Yeah. Water moves from low concentration to high concentration. Right? Think of the high concentration as like it's lacking water. It's drier, so it will suck in water to dilute itself. Right. So what happens here is that the pure water gets sucked into the salt water and moves this way. Right. So there's water gushing across the semi-permeable membrane into the salt water. And so this level will go down and this level will rise up because of osmosis. Now, suppose you want to stop this osmosis in its tracks. To do that, you'll have to apply a counter pressure on this side, right? To stop osmosis. The amount of pressure that you need to apply to stop osmosis from happening is osmotic pressure. All right, so this is osmotic pressure pi. Cool. All right, almost done. Now let's look at a couple of questions. This is a very realistic question. I always do this. To boil pasta, a pot containing, 200 grams of salt. So that's a lot of salt, but it's okay. 200 grams of salt, table salt, NaCl, is added to a pot containing let's say 1,000 grams of water. Calculate the new boiling point. Calculate the new boiling point of the water. The answer to this question will give you one reason why we salt our pasta waters. Okay. All right, so which of the 4 equations do I use? Yep, first one, boiling point. Cool. Delta TB equals I times KB times M. And since we want the explicit temperature of the new water, let's expand this delta. It's boiling point of the solution minus boiling point of the solvent, which is water, equals I times KB times M. Let me just give you what the KB value here is. Oh, by the way, the constants KB and KF only depend on the solvent, not the solute. And so we're going to look up the KB.
Sorry, can you say that again?
KB, the constants KB and KF depend only on the solvent. So if you have water with salt, water with sugar, water with whatever, you're going to use the KB for water. It's independent of salt, sugar, or whatever you're adding to the water. Okay, KB for water is 0.512. Don't know if you need to memorize that. Hopefully not. Cool. What is the boiling point of regular water, pure water?
A 100 degrees Celsius.
100. Yep. Water freezes at 0 Celsius, boils at 100. Okay, so let's start filling in information here. This is what we need to calculate. So just gonna write TB of solution minus 100. Oh yeah, in these equations, you have a difference of temperatures, delta T. So it doesn't matter if you use Celsius or Kelvin. Right, okay. What is I for salt? NaCl. Two, good. 2 pieces. KB, we've said, was 0.512. And of course, the last thing that you need is to calculate the molality. I'm going to give you the molar mass of NaCl real quick. It's about 58. About 58. Just roughly speaking, how many moles of salt do you have? You know what? Let me change the grams of salt to 240 to make it better. $240 grams of salt. Molar mass is 58. What is the number of moles, roughly speaking? 4, right? 58 is about 60. 240 divided by 60 is about 4. Yep. So about 4. Just gonna be lazy and do that. So molality is moles of solute divided by, or you can calculate molality separately first. Kilograms of solvent. It's nice here. It's 1,000 grams. Kilograms is 1. So molality is about 4. All right. So boiling point of the solution is going to be, I'm going to add 100 to both sides plus whatever this mess is. This is about half, 0.5 times 4 is about 2. 2 times 2 is about 4. I'm approximating, you do the exact numbers. So that is about a 4-degree rise in temperature. Water now boils at 104 degrees Celsius. Your pasta will cook faster. That's a higher temperature. This is partly the reason why if you're trying to saute vegetables, if you salt them, they lose water faster. The two things happening, it's higher temperature because of the addition of solute, but also osmosis, sucking water out of your vegetables. So both, Professor Wright and I once debated why adding salt to sauteing vegetables makes them cook faster. She said it's osmosis. I came up with, oh, it's a higher temperature. I think they're both factors that contribute to it. Okay, so imagine the same question with freezing point, nothing changes. And I'll give you 2 more and then we're done. All right, so this is a classic. When 5 grams of a mystery protein is added to 100 grams of water at 25 degrees Celsius, the osmotic pressure is, I always forget whether to make this a big value or a small value. Okay, let me think real quick. Pi equals I D. Okay, I should make it small. 0.02 atmospheres. Determine the molar mass of this mystery protein. This is a real technique, by the way. If you isolate successfully a new compound, but you have no idea what the molecule looks like, well, one key piece of information about it is its molar mass. Since you don't know what the molecule looks like, you can't directly calculate what the molar mass is. And so you use an indirect method like this. You make a solution out of it and then measure the osmotic pressure and then work out the molar mass. Powerful. So first question, quickly tell me what I is. Yep, Pavel.
In this case, I should be 1 unless it's a multi-part protein that breaks up into subunits.
Yep, true. Proteins are covalent compounds. They don't break up. So I must be 1. Okay. So I'm gonna write down the osmotic pressure equation, I times RT times big M. What R value are we gonna use here? The 8.314, the 0.0821. What do we have involved? Energy or liters? Can you find liters anywhere in here? Stuffed inside some things, maybe?
We know the mass of a kilogram. I mean, we know the volume of a kilogram of water at 250 degrees Celsius.
Yes, but in this equation, do you have anything that involves liters?
The molarity.
Molarity, yep. And so you've got to use the 0.0821 in this case. Okay. All right, so tell me, what do I know in this question? What can I start by filling out? Yep, Christopher, go ahead.
You know, osmotic pressure is 0.02 atm.
Cool.
You know, I is 1.
Yep.
You know, the gas constant.
Mm-hmm.
Temperature is in Kelvin, so 298.
Yep.
And then you're trying to find the molar mass. Oh,
molar mass, yes.
You know, like moles over 0.1 liters of water.
Okay, I like that. So basically you're trying to expand molarity and write it in terms of its pieces. Right, okay. What goes on? Let's start by filling out the bottom of the molarity equation. So liters of solution go on the bottom. Yep, go ahead.
So the density of water is 1.
Yep.
If you have 100 grams, that's 100 milliliters, which is 0.1 liters.
0.1 liters divided by 1,000. Good. That's a volume of water, but we don't expect the volume to change much on addition of the protein. So we're using the approximation. Solution is approximately volume of solvent. Yeah, so that's good. I have the bottom. Do I have the moles of the protein? No. How do you calculate the moles of the protein? How do you calculate moles of anything? Pavel, go ahead.
You need the molar mass, ideally.
Yes.
Provided to, or some kind of value of some kind of method of obtaining the molar mass.
Sure. But so the molar mass goes on the bottom. What goes up top?
The mass, the known mass.
Known mass. Do we have that?
Yes. 5 grams.
5 grams. Okay, so I'm just going to stuff that whole thing in here. Now I should be able to solve for molar mass because that's the only unknown in this equation. Okay. All right. So writing this slightly differently, 1 times doesn't matter. I can push the molar mass downstairs, so it's in the denominator now, right? And then if I bring the molar mass on the left-hand side and push the 0.02 on the right, you get 0.0821 times 298 times 5 over 0.02 times 0.1. Calculate this number real quick. About 61,000 grams per mole. Huge, right? Proteins are huge. So this is a realistic mass of a protein. That's why I, in the beginning, I said, I always forget whether to make osmotic pressure really large or really small to come out with a realistic number. Yeah, it worked out great. I judge my recitations on this question. It's like, if it comes out to be a large number, I know I've done well, and it's going to be a good semester. If I mess this up, I'm like, oh, bummer. Better luck next time. Anyway, okay. Last question. And this relates to the vapor pressure stuff. A solution is 180 grams water and what was it? 40, 50, 58.4 grams NaCl. Molar mass of water, I'm just going to give it to you, is 18. NaCl is 58.4. A, calculate what's called the partial pressure of water in the solution. No. Calculate the vapor pressure of water in the solution. B, calculate the vapor pressure of salt in the solution. That's right. I see some heads turned up when I asked that question. There's something wrong with question B. Something doesn't make sense. That's exactly the point. And then lastly, calculate the total pressure. All right, the question that we have is as usual. P of any component A is I times hold on. I times the original pressure times chi A. And we're doing this at 25 degrees Celsius. I'll give you the vapor pressure of water at 25. Okay, 0.0313. ATM. Okay, cool. So easy, just plug and chug. The pressure, the vapor pressure of water on addition of NaCl is going to be given by I. By the way, this I refers to I for A. So the component that you're talking about. Water, what's the I value for water? 1 because it's covalent. Yep. What is its initial pressure? Right there. I've given it to you. 0.0313. And what is its mole fraction? How many moles of water do you have? The good numbers.
10.
10. And how about NaCl?
1.
1. So 10 plus 1, that's a total of 11. And you're done. Right? So basically the idea is you apply this equation to each component. All right, part B, same thing. PB equals I, B, P naught B, and then chi B. What is the vapor pressure of salt? If I just have a bunch of salt in a beaker, what is its pressure? For pressure to build up, your substance first needs to evaporate, right? It needs to go from whatever phase it's in to gas phase.
Lower pressure?
Huh?
Is it the pressure lowered?
Is the pressure lowered? What is the pressure of just salt sitting in a container? Nothing, right? Salt doesn't evaporate. If it doesn't evaporate, it doesn't build up pressure. And so salt being a solid that doesn't evaporate, this thing is 0. And so the entire thing is just 0. Right? Solids don't evaporate. The initial pressure of solids is therefore always 0.
Sorry, this is a dumb question.
Mhm.
Obviously for one's obvious things, that's clear. For other substances, how would we determine that they don't evaporate?
The only rule you have is that solids don't evaporate. That's all. Now imagine if it was a mixture of water and alcohol, ethanol. Both of them have initial vapor pressures on their own. They'll either be given to you in the question, or that will be the thing that you would solve for. So you only make it 0 for solids. That's all.
But there are solids that evaporate.
Yes, sublimation. You're not gonna see a question that involves a solid that sublimates. But it is true. You're right. So let me change that. Most solids don't evaporate. Some do. All right, so what is the total pressure of the solution? That's very simple. Add up the pressure contributions due to each component, and you're done. So the pressure total is going to be the pressure of water in solution plus the pressure of salt in solution. So that's whatever this number came out to, plus 0. So it's just the pressure due to the water. If you had a water ethanol solution, this would be a non-zero number, and you would add that up. Okay. Just to summarize this, if you have two components, A and B, to a solution, the pressure of A is, so the pressure total for the whole solution is given by the pressure of A plus the pressure of B. The pressure of A you calculate by applying this equation. So that's IA times P naught A times mole fraction of A. And the pressure of B you also calculate by applying the same equation. So IB times P naught B times chi B. That gives you the total pressure of a solution containing two components, A and B. That's the idea. That's it. End of chapter, I believe 12, right? Or 11. Probably 11. Yeah, it is 11. Chapter 12 is kinetics. Yeah, fun stuff coming up. I think I probably missed out on Henry's Law, but that is like super easy. Not really worth going over. It's plug and chug. But yeah, I went over all the more difficult stuff. Cool. Any questions?
Would you mind sharing these notes?
In addition to the recording?
Or that's okay. We just record
Yeah.
fine.
Did you have a hard time reading the notes in the recording?
Oh no. I just like wanted to print it out, but that's okay.
Oh, I can always give you a PDF of this. Sure, no problem. If you can understand my handwriting, terrible handwriting. All right, cool. I'll see you guys next week.
Thank you.
Yep,
Thank you.
no problem.